This page introduces a critical architecture extension called TrustZone. This is ARM's hardware-based security solution. Think of it as a way to create two separate, isolated environments or worlds on a single processor. As you can see, these are called the secure world and the normal world. The core idea is to run your regular operating system, like Android or Linux, and all your everyday applications, like games, browsers, and email clients, in the normal world. This is the left side of the diagram. But for operations that handle very sensitive data, like mobile payments, fingerprint authentication, or managing digital rights for movies, you need a much higher level of security. That's what the secure world is for. It runs a separate, smaller, highly secure operating system, often called a trusted OS, and specific trusted applications or services. So, how does the processor keep these two worlds completely separate? The first point mentions that each world has its own vector table and page tables. This is key. It means they have entirely separate memory maps. The normal world's operating system has no idea that the secure world's memory even exists. It's like having two separate computers on one chip, ensuring that a bug or a virus in a normal world application can't access or corrupt the secret data in the secure world. Now, how do you communicate between these worlds? You can't just jump from a normal application into a secure one. There needs to be a very controlled entry point. This is where the monitor mode comes in. It acts as a gatekeeper. When a normal application needs a secure service, it executes a special instruction that triggers a switch into monitor mode. The secure monitor, which you see at the bottom of the diagram, is a small piece of highly privileged code that manages the transition. It saves the state of the normal world, switches the processor into the secure state, and then allows the trusted OS to run. It's the only bridge between the two worlds, and it's heavily fortified. This isolation is enforced at the hardware level using a special NS attribute or non-secure bit. Every transaction on the system bus, every memory access, is tagged as either secure or non-secure. The memory system then checks this tag. If the processor is running in the normal world, it can only access memory addresses marked as non-secure. The example here is excellent. S0x8000 is treated as a completely different physical memory location from NS0x8000. This means that even if a malicious program in the normal world knew the exact address of a secret key in the secure world, the hardware itself would block the access, generating a fault. Finally, this security extends to debugging. It's possible to configure TrustZone so that a hardware debugger can see and control the normal world, but is completely blocked from accessing or even seeing the code and data inside the secure world. This is crucial for preventing attackers from simply pausing the processor and reading out secrets from memory. Following our look at the security extension, TrustZone, let's now dive into another critical feature: large physical address extensions, or LPA. So, what problem does this solve? Think about a standard 32-bit processor. The maximum amount of memory it can address is 2 to the power of 32, which comes out to 4 gigabytes. For many years, this was more than enough. But as computing demands grew, especially for servers and high-performance devices, 4 gigabytes became a major limitation. The question then is, how can a 32-bit system use more than 4 gigabytes of physical RAM? This is where LPA comes in. It's an architectural extension that allows the processor to access a much larger physical memory space. As the first bullet point states, LPA introduces a new, long descriptor format for page tables. Remember, page tables are what the Memory Management Unit, or MMU, uses to translate the virtual addresses used by software into the actual physical addresses of the RAM. To point to a larger physical address space, the entries in these tables, called descriptors, need to be bigger. The new long descriptor format uses 64-bit descriptors. This larger size provides enough room to specify a 40-bit physical address. And what does a 40-bit physical address space give us? It's 2 to the power of 40, which is a massive 1 terabyte of accessible memory space. So, with ALPve, a program can still run using its familiar 32-bit virtual addresses, but the hardware can map them to physical RAM anywhere within that huge 1 terabyte space. Now, a key principle in architecture design is backward compatibility. You don't want to introduce a new feature that breaks all existing software. That's why the second major point on this slide is so important. The original 32-bit short descriptor format is still supported. This means an operating system can choose whether to use the new ALPve format or stick with the classic one. This is configurable through a specific bit in a control register, the EE bit in the translation table-based control register. Think of it as a switch that turns ALPve on or off. The slide also mentions that with this older format, you can use 16 megabytes memory supersections to help map onto the 40-bit address space. This is a mechanism for handling large, contiguous blocks of memory. However, the long descriptor format is the more modern and flexible way to utilize the full potential of ALPve. In short, ALPve is a clever and crucial extension that effectively breaks the 4 GB barrier for 32-bit ARM architectures, paving the way for them to power systems that require very large amounts of physical memory. Building upon the security features of TrustZone, ARM processors also include extensions for virtualization. The core idea behind virtualization is to support running multiple guest operating systems on a single processor, all at the same time. Think of it like running both Windows and Linux on your laptop simultaneously, but here we're doing it on an embedded ARM chip. To make this happen efficiently, ARM introduced a new processor mode called hypervisor mode. The hypervisor is a special, highly privileged program that acts as a manager or a host for the guest operating systems. If you look at the diagram, you can see how this is structured within the normal world. At the bottom, you have the secure monitor, which we've seen before. On top of that, in the normal world, sits the hypervisor. And on top of the hypervisor, you can have multiple guest operating systems, each with its own set of applications. So, how does the hypervisor manage these guest OSs? One of the most important mechanisms is called two-stage address translation. This might sound complicated, but let's break it down. Normally, an operating system translates virtual addresses used by applications into physical memory addresses. In a virtualized system, this happens in 2 steps. First, the guest OS translates a virtual address into what it thinks is a physical address. But it's not the real one, it's an intermediate physical address. Then, in the second stage, the hypervisor takes that intermediate address and translates it into the actual physical address in the system's RAM. This 2-stage process is critical because it allows the hypervisor to keep the memory of each guest OS completely separate and isolated from the others, preventing one OS from interfering with another. Another key role of the hypervisor is to handle exceptions. When a guest OS tries to perform a privileged operation, like accessing a hardware device directly, the processor can trap this request and hand control over to the hypervisor. The hypervisor then acts like a referee. It can inspect the request and decide what to do. It might grant the access, deny it, or manage the hardware on behalf of the guest. This ensures that the guest operating systems can't disrupt the whole system and allows the hypervisor to share hardware resources between them in a controlled way. It's important to remember that all of this virtualization activity happens within the normal world. The secure world, with its trusted OS and trusted services, remains completely separate and isolated, managed by the secure monitor. The hypervisor itself runs in the normal world and does not have access to the secure world's resources, maintaining that fundamental security boundary we learned about with TrustZone.